Let's have a look at the contents of the fourth module. Basically, the fourth module deals with the semantic analysis phase. As we know, semantic analysis is the third phase of the compiler. The major topics are syntax directed translation and type checking. Let's see each of the topics in detail. So far we have seen some grammars, and for the grammars we had seen different parsers. But when we practically implement a compiler, this grammar alone is not enough. So along with this grammar we will add some informal notation, and we call this informal notation as semantic rules. So this grammar plus informal notation is very much necessary for evaluation of a parse tree. Let's make the idea more clear. The output of the syntax analysis phase is the parse tree, right? But this plain parse tree alone is of no use for a compiler, because it's like a simple plain tree structure. It don't have any additional information regarding the evaluation of the parse tree. Let's take an example. Imagine there is a new machine out in the market and you don't know how to use it. Normally all machines will come with a user manual which contain information regarding how to use it, how to handle the different components of it, how to evaluate it, etc., right? Imagine if the user manual is not present there. So in a way we can say the machine is of no use since we don't know how to use it. Likewise, this is same for a compiler also. So the parse tree along with some informal notation is needed for the proper evaluation of a parse tree. This is a very basic idea. One more thing. When we say about the phases of compiler, the third phase of the compiler is the semantic analysis phase, right? The input to the semantic analysis phase is the parse tree. That is the output of the syntax analysis phase. And the output generated by the semantic analysis phase is called as semantically verified parse tree. As the name says, it verifies the semantics of the parse tree. Literally we can say it verifies the meaningfulness of the parse tree, and this is done with the help of certain set of rules called as the semantic rules. Okay, now let's see what this syntax directed translation is. Syntax directed translation, and this is the first topic in this chapter. So a grammar along with certain semantic rule is said to be as SDT, or syntax directed translation, and this will be very useful for a compiler for doing many things in parallel along with parsing. Now let's see an example for an SDT. So we have an example here. We have a grammar, and for each productions of this grammar we have certain actions to perform, and these actions are called as semantic actions. Now let's see an expression and see how SDT perform evaluation of this expression. Okay, so the input expression which we are giving to the STD for evaluation is 1 plus 2 into 3. And the procedure for evaluation is first we must construct the parse tree for the given grammar. I already have constructed that. You know the construction of a parse tree, right? Since there is no point of discussing that one. Now substitute the values of this expression to the tokens. That is, if we substitute the values of token to values of this expression to tokens, that is 1 plus 2 into 3. That is 1 plus 2 into 3. Here we can see that num is nothing but a token like id, and 1, 2 and 3 are lexical values. Lexical values are nothing but they are actual values given to the tokens, and this is first step. In step number 2, we perform tree traversal from top down to left right. That is from top to down, from the left to right, right? Okay, one more thing. See, whenever you see a reduction, you must carry out some action specified in this semantic rule. So whenever you see a reduction, so like num is being reduced to f, f is being reduced to t, t star f is being reduced to t. Whenever you see a reduction like this, you need to perform a specific action which is mentioned in the semantic rule. Let's see the example of this reduction. That is, num is being reduced to f. So in the semantic rule, we can see that f is being associated with a variable called value. This is also called as, this value variable is also called as an attribute. So we say the attribute associated with f is value. That is, when we travel from top down to left right, the first reduction that you will see is this number is being reduced to f. So look for the reduction in the production. So that is number is being reduced to f, and look for the action that you need to perform. That is, what is the attribute associated with f? The attribute associated with f is f dot value, right? So f dot value is equal to, what is written there? Num dot l value. Num dot l value is the lexical value, and here the num dot l value is 1. So we may substitute the value of num dot l value as 1. So f dot value is equal to what? Num dot l dot value, that is 1. Then we go further up. You may see there is another reduction, that is f is being reduced to t. That is, f is being reduced to t. So look for the semantic rule that we have, that is t dot value is equal to f dot val. So we may substitute that t dot value is equal to f dot value. F dot value, we already have that f dot value is equal to what? 1. Now again, going further up, you may see there is also one more reduction, that is t is being reduced to e. So, and look for the particular semantic rule that we have, that is e dot value is equal to t dot value. So e dot value is equal to what? t dot value. T dot value, we already have that value, that is 1. Done. Going further, you can observe that here is no reduction, that is e plus cannot be reduced to e. Now the next reduction that you may observe is over here, that is num can be reduced to f. So when we have the production, num can be reduced to f, and the semantic rule that we have is f dot value is equal to num dot l value. That is num dot l value here is 2, and we may write like f dot, let me take my pen. Okay, so f dot value is equal to num dot l value. Num dot l value here is 2, right? Now the next reduction that you can observe is over here, that is f can be reduced to t, right? So the production that we have, the semantic rule that we have for this particular reduction is t dot value is equal to f dot value. So you may simply write like t dot value is equal to f dot value. F dot value here is 2, right? Okay. Now going further, you can find here is no reduction, that is t star cannot be reduced to t, right? So the next production that you may observe, next reduction that you may observe is over here, that is num can be reduced to f. Okay, we have the grammar rule for that, that is num can be reduced to f, and the semantic rule there, that is f dot value is equal to num dot l value. Num dot l value here is 3, right? Going up, you may see the next reduction, that is t star f can be reduced to t, right? You may see the action, that is t value is equal to t value into f value. If you observe, there is a confusion between the left side t value and right side t value, right? To avoid that, I am just writing the right side t as t1. Okay, so let me write that. So I am just writing the right side t as t1. Here also I am writing t1. So it doesn't mean that this t1 is a different variable, but just to distinguish between these two variables, I am putting as t1. So the semantic rule is t dot value is equal to t1 value into f1 value. We have the t1 value as 2 and we have the f value as 3. So 2 into 3, that is t dot value is equal to t1 value into f value, that is 2 into 3, 6, right? Okay, the last reduction that we may observe is e plus t can be reduced to e, right? And when you see the action, that is e value is equal to e value plus t value, right? So here also, just to distinguish between the left side e and right side e, I am writing the right side e as e1. Let me write that. So right side e as e1. Okay. So we have E value is equal to even value plus T value, right? So even value we have as 1 and T value we have as 6. So E value will be 1 plus 6, that is 7. Let me write that. E value is equal to 1 plus 6, that is 7. That's it. We have completed. So we can say we have evaluated the expression using SDT, right?